Homework busy? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
So here, I think it'd be better to draw what is going on. So we have this electron here. This is accelerated by a V accelerating potential. And we have this delta X of the field here. And this field has a magnitude of E. And it is deflected. So we have this deflection here. And we have this vertical displacement here. This vertical displacement is 11 centimeters. And then this right here is 22 centimeters. And then this, we have an angle here of 30 degrees. And I think, yeah, so this is exactly what's happening. We have some givens. So a mass of an electron is 9.11 times 10 to the negative 31st kilograms. We have the accelerating potential of 9 kilovolts, or 9,000 volts. And we know that the potential energy equals the kinetic energy in the beginning. So let's evaluate this before the field. So this is everything before it even approaches the field. We simply know that the accelerating potential accelerates this. So we have a potential energy converting into a kinetic energy. So we can say that EV equals 1/2 mvx squared. And we find that Vx is going to be equal to 2ev over m to the 1/2 power. Now, we're not going to solve for this just yet. It's actually easier just to keep it in variables and then solve at the very, very end. So now let's evaluate the field. So everything that goes on in the field. So we have delta x of the field. This is going to equal Vx times the time in the field. So we know that the time in the field is going to be equal to delta x in the field divided by V sub x. We know that sigma f in the y direction is equaling the charge on the electron times E. And this will equal the mass times the acceleration in the y direction. So we can say that the acceleration in the y direction equals E times the magnitude of the electric field divided by the mass of an electron, yes. We know Vy equals Vy initial plus AYT of the field. So we can say that this is going to equal 0. And we know that this is going to equal E times the magnitude of the electric field times delta x of the field divided by m of Vx. So at this point, we have evaluated everything in the field. Now we're going to move on to the screen. So this section will be our screen. And we have that delta x of the screen equals Vx times delta t of the screen. So again, we know that delta t of the screen is going to be equal to delta x of the screen divided by V sub x. And we know that delta y of the screen now will equal Vy of delta t of the screen. And we know that this is going to be equal to Vyx of the screen divided by V sub x. Now at this point, we can attempt to solve. We know that delta y of the screen divided by delta x of the screen equals V sub y divided by V sub x. this is going to equal the charge of the electron times the magnitude of the electric field times delta x on the field divided by mv x squared. So we know that E is going to be equal to delta y of the screen, mv sub x squared divided by delta x of the screen times delta x of the field. Now we're going to have to plug in this equation into this equation. So now we have E equals 2v delta y of the screen divided by, again, delta x of the screen times delta x of the field. And at this point we can solve. So this is going to be 2 times 9,000 volts times 0.11. And then we'll have 0.22 times cosine of 30 degrees, and then 0.028 delta x of the field. And we find that E, the magnitude of the electric field, is going to be equal to 3.71 times 10 to the 5th volts per meter. So this would be our final answer. That is the end of the solution. Thank you for watching.